Welcome to the 7th lectures in Lattice Boltzmann methods. So today we are talking about boundary and initial conditions. For this we first have to start with the scaling of physical and numerical units. This is what we are doing first. So this is something that is in principle relatively simple, but has to be, but is still a subject of a lot of confusion. So first of all, one thing that we have to take into consideration, and it is very important, that during the simulation with Lattice Boltzmann, we never use physical units. I know that in finite element methods this sometimes happens, so that we actually use the variables in terms of, say, the bending, in terms of, say, the displacement in terms of meters, yeah, or in centimeters or something like this. So this never happens in Lattice Boltzmann. We're always using the units, the so-called lattice units, which is given by the grid spacing delta x, which of course now is something that is given in meters. So this brackets means this is the unit of delta x, and delta t, which is then given in seconds. But we express everything in these lattice units. So now here we write the physical things like the velocity with this asterisk, yeah, velocity u asterisk, and the physical pressure p asterisk. This is the velocity and the pressure given in physical units. And they then have to be expressed in terms of these lattice units. So we have lattice, for example, the lattice velocity. So the lattice velocity, u, now this is of course given in delta x by delta t. And so, the lattice units, u, so we compute this velocity vector u by, let's say, if we are in 2 dimensions, then we sum over the indices I and j, and we have a vector I and j, because this is going to be a vector. Why did I write this bracket? Sorry, this was of course nonsense. And this into fi and j, and here we come delta x by delta t. So in practice, what we often do, because we all know that we are using lattice units, in practice we often don't write them, or we consider them to be 1. So that delta x is 1 and delta t is 1. But this is implicitly assumed here, and of course this is not a good practice for teaching, but at the end everybody is doing it in this way. So, but you have to understand they are still present here, yeah? So now we have to do our scaling, because we get our real-world problem. We want to have our velocity u, and we get this from u asterisk. They are the same. They are supposed to be the same, given in different units. And now the way we write this is by, let me take a different color, delta t by delta x, returning to my color, in delta x by delta t. So you see this is doing nothing, right? Yeah, but this is used to do this transfer. So what we want is this u to be in the unit delta x by delta t. So what we are going to do is we keep this, and we will replace this. So we will replace this with what we have in meters and in seconds. So, for example, and now I take the red color because this is what we are going to replace. The delta x is 1 millimeter. So one grid spacing is, we design our grid so that one grid spacing is 1 delta x, and that 1 delta t is 1 microsecond. So this is actually something that makes sense in this setting. And now we have the velocity u star. Now I just write it not as non-vector because it just is one value. Say it's 0.1 meters per second, right? So now we write this in our physical, in the lattice units. So it's 0.1 meters per second. Now here we replaced our delta t. Our delta t is 10 to the power of -6 seconds. And this divided by delta x is 10 to the power of 3 meters times delta x and delta t. So the last one we keep, yeah, and this obviously is 10 to the power of -4 delta x by delta t. So this is the way we do it, right? So it's not difficult, but it's often some way of confusion. And then later, what you will finally find, because this is the number that you put in your code, and when you put it in the code, the delta x and the delta t is usually assumed to be implicit, yeah, so you don't write it down in your code. Then the thing that is probably a little bit more confusing is the lattice pressure. The reason why this is confusing is because in Lattice Boltzmann you don't actually use pressure, but you use density. So this is important to know. Pressure is expressed in terms of density in LBM. And the other thing to know is that the absolute pressure, I mean, this is now from the continuum theory. Yeah, so you know this when you look at the Navier-Stokes equation, then the absolute pressure does not appear in the Navier-Stokes equation. There we only have relative pressure because there's only the derivative of the pressure, not the pressure itself. And this is also the reason why when you solve the Navier-Stokes equation, you often do something like you put the pressure at the outlet to 0. Yeah, so because modeling-wise you can do this. In reality, I mean, this is not physically correct, because if you put pressure to 0 means you put a vacuum there. Then, if there is a vacuum, then the mean free path would be infinite. So you would have an infinitely large Knudsen number, and the Navier-Stokes equation would not be correct. But since the Navier-Stokes equation doesn't know about the Knudsen number, if you just do it, it works, right? So what we do in Lattice Boltzmann in Lattice Boltzmann is to use the equation of state instead for specifying the pressure, and this is in Lattice Boltzmann, this is actually a linear function. So what do we mean by equation of state? Equation of state is how the pressure is related to the density, and this is just by multiplying it with the speed of sound squared, yeah? Which is can be expressed. So the speed of sound, of course, is a function of the temperature, but the temperature is considered to be a constant in Lattice Boltzmann. So since the pressure is related to the density, what we have to do is to specify the density in order to set the pressure. And because we only need to have a relative pressure, so we have a relation between pressures or different pressures and their densities. So suppose we have a physical pressure and we want to have this, and we have a physical base pressure, then this relationship would be equal to a density and a base density. So what we do in Lattice Boltzmann is we set the base or reference density to 1. Yeah, this is just for simplicity. By the way, this is statisticians like to do this because we are dealing with the distribution function, and they like distributions to be the integral to be equal to 1. Yeah, so this is why they say, okay, we just say the density, which is the zero moment, yeah, is 1. So then the base is 0, is 1. And this means that we can express our density as a P, physical P divided by a base pressure, and this gives us now our density that we have to take. And of course, this rho 0, this is constant. This is the constant part. This is the constant part which in the asymptotic analysis comes with the with rho 0. Yeah? So for example, suppose we have a tube, and in this tube we want to apply a pressure difference where we have a pressure P1 and a pressure P2. Now these are absolute pressures, yeah? So this would be, and this has some length, say this has a length L also, right? So, and then we have a pressure-driven flow in this. And say, for example, the delta P star would be 100 pascals. And we say that our base pressure would be 1000 hectopascals, so which is 10 by the power of 5 pascals. Then what we do in Lattice Boltzmann is we have to specify a rho 1 and a rho 2, and what we do, because this rho 2 is the outlet, say P1 is, so the flow is going this way, right? So if P is rho 2 is the outlet, what we can do is to say rho 2 is our base row and set this to 1. And this means that row 1 divided by row 0, which of course is 1, is delta P star plus P 0 by P 0, right? And this would give us a pressure or density in the inlet as 1.01, right? So it is just the difference in the absolute, the difference in the absolute pressure between inflow and outflow is the difference between, the ratio between these pressures is the same as the ratio in the densities, right? And so we can set our densities instead of setting the pressures. Okay, I'm not completely sure I can finish the lecture today because we have this gap of 20 minutes in the beginning. Now we come to the initial conditions, so all important stuff for your so if you have any questions, this is why we come here, yeah? Then please tell me. So initial conditions. Initial conditions cannot usually be 0, at least not for the density, because otherwise we generate a vacuum. So this is one of the common mistakes that I see appearing in the very first time somebody is implementing these things. It has become less common because nowadays nobody is implementing it first of all. They just take something from the internet, I notice, because there are so many implementations already. Yeah, so I'm thinking about a way how to avoid this, but anyway. So what we need here, instead of for the Navier-Stokes equations, we need initial conditions for all moments that we specify, right? So we need more initial conditions than we have for the Navier-Stokes equation. This also has some implications, which we come across below. So Navier-Stokes equation requires only for, let's say we don't have temperature in the Navier-Stokes equation, because we are looking at the incompressible one. Then we only need initial condition for the velocity and the pressure. Now here we need all moments. So what are we usually doing? So the first and simplest way to initialize Lattice Boltzmann fields is by using the equilibrium methods. And even though this is not perfect, this is the way it is usually done. Yeah. So say we are given u of x and 0, so this is the time 0, right? And now a density which we usually compute from the pressure at position x and 0. Then what we very simply do is we compute the local equilibrium that you need to compute anyway for your BGK collision operator if you are using this. So we locally in every point, we compute the equilibrium and just set this as the initial condition. So this is the distributions Fij, or 3 dimensions Fijk, U and rho, and we compute them from the Maxwellian, for example, or whatever, the same way we compute them in the collision operator. So, the good thing, this is simple. This works. Yeah, and this is why it's also done. So we always have, as we learned, we always have to specify two good things. Now I'm only saying one bad thing. The second moments are wrong. See, I'm trying to write wrong, but the way I write wrong is wrong. So they are wrong if the initial conditions or the initial condition has a gradient. So we spend a lot of time with this asymptotic analysis to see that the moments contain information on the gradients of, for example, velocity and other things, right? And so if our initial condition is one that is not constant everywhere, but has some gradient, then this initial condition will not be correct if we set it by equilibrium. And this means that in the beginning of the simulation, we have something that is not correct. So why does it usually make sense to still use equilibrium boundary condition in many cases, or in what cases? Well, what you're often interested in is the long time behavior, right? Or a steady state, or behavior after a long time. So you take into account the beginning of the simulation may not be physical. And then you can set these equilibrium boundary conditions, but there are the cases where the timing is very important. So when you want to set an initial condition and you want to see how does this flow behaves from here onward, right? And if this is what you're interested in, not having the right second moments will kill your simulation. Yeah? So then sometimes, so depending on what is your objective, for example, in the homework your objective is to compute the lift and the track. So what you would usually do, you run the simulation for a number of time steps, then you see, okay, now we get to a point where nothing changes anymore, so we cut off the initial part and we do the averaging over the rest, and we don't care about the initial condition. Yeah? You have an initial condition where you want to see what is, so for example, you want to do a weather forecast, you get your information from a satellite, so this is the initial condition. So how will this behave in the next 5 minutes, next 2 hours, right? So these are two different tasks. So what we are very often happy with equilibrium methods, but sometimes we need these, okay, I should write this down. Sometimes we need some correction. So what we get wrong is we have the wrong dissipation in the initial phase if we do this. So, and therefore we have a different method, or in addition to this, we have a second moment correction, non-equilibrium correction. So we actually take our first and zero moments the way we just described, but in addition to this, we set also a non-equilibrium part for the initialization. And this now comes from the asymptotic analysis. So we are always here dealing with the Navier-Stokes level. Yeah? So the Navier-Stokes limit requires, as we have discussed last year in detail, that the second order moments they should be second order in diffusive scaling, of course, second order consistent. In epsilon. Okay, epsilon is delta x. And third order moments to be first order only. So first order, this is a good thing because this, for the third order moment, this requires only that the equilibrium is correct. Yeah? So we do not need to correct the third order moments. We could also do this, then it would even be more accurate, but it's not required from the asymptotic point of view if we are fine with second order consistency. So what are the second moments from the asymptotic analysis? So we have the M20 over bar. So this is the average between the pre and the post-collision states. This is supposed to be the M20 equilibrium to second order, minus 1 over omega minus 1/2. And then we have here 2/3 dx ux, and I'm not writing lattice units here anymore, and rho to the order 0. And m, of course, M02 over bar, second order will be M02 equilibrium to second order minus 1 over omega minus 1/2. 2/3 dy uy to first order into the constant parts. And then we have the other second order moment is M11. Also to second order is M11 equilibrium that we get from our equilibrium initialization, minus 1/3 1 over omega minus 1/2. And this is dx uy to first order plus dy ux to first order. And I've forgotten to write rho. So, okay, I mean, rho 0, as we specified, is 1. So I can actually omit this. So, as I just said, third order is easy, because M12, this is one of them that we have, is equal to 1/3 rho 0 ux, which is exactly the equilibrium. Yeah. So this would be M12 equilibrium to first order, and M211 is 1/3 rho 0 uy, and this is M21 equilibrium 1. So not equilibrium for third moments. So we don't have to correct them. So now, if we set our initial condition, and I now assume that we set the initial condition, for the pre-collision term, so we could also have it for the post-collision term, then we have to start with the streaming. But now we assume we start with a collision. So if we start with a collision, then of course we have to have pre-collision initialization. And then these cases that I specified here would look like this. And I now don't write the order because I'm now writing what we have to specify here. So we set the M20, we just set them to their equilibrium part, minus 1 over omega. So this is what comes out for the pre-collision state, times 2/3 dx ux, and M02 is M02, now 02 equilibrium minus 1 over omega rho 2/3 dy uy, and the last one that we have to specify is m11 is equal to m11 equilibrium minus 1 over omega rho divided by 3 dx uy plus dy ux. So if there is a gradient in the system and you know this gradient, you have to compute it and put this into your initial conditions. Okay, now we are more than half of the time over, and now we try to come to the boundary conditions. We don't have the time to talk about all boundary conditions, but we'll mainly focus on velocity boundary conditions here. Yes, so again, we have kind of a problem because the Navier-Stokes, I have a problem with my computer apparently. The Navier-Stokes boundary conditions, they cannot be set directly because here we don't have to set the velocity and the pressure, but we have to impose boundary conditions at our populations. So the populations have to be imposed, and they of course have a different meaning than velocity and pressure, right? Okay, so there's in general a difference between so-called node-based and link-based boundary conditions. And in both cases there are many of them, but I just give very few examples. Yeah, so this is not comprehensive. I just tell you what all is possible, and we start again as always with our characteristic diagram where we have x here and t here, and these are now our lattice nodes. I should probably have drawn it with a bigger spacing, but okay. Let's face it, next time I draw it with a bigger spacing. So say here's our boundary. Here's the boundary. Yeah? So what I want to indicate here is that the boundary is on the node. Let's say this is now the incoming distribution. I'm not going to draw all of them. This is the incoming distribution. Post. And this is the outcoming distribution. So say this is post-collision. So post-collision is always F star, right? And we have pre-collision, which we call F. Okay, so the boundary is on the nodes are on the boundary, and then there are here alone, there are two approaches, of which we look only at one in detail. Two approaches. The first one is to replace all populations on the boundary. For example, with equilibrium. Okay, actually, I know that you didn't do this, but this was my expectation or for your homework. yeah, or for at least for in some cases in the homework, because there are different cases. So what you can do is you just take the nodes on the boundary, and you want to have a specific velocity and a specific pressure there, and you just impose this by setting the equilibrium distribution to this node, right? So you override it every time step, and then you have a given velocity and a given pressure at this boundary. Yeah, it's not a good boundary condition, but for many cases it works. So this is number one that you can do, and would be completely sufficient for our exercise here. And the other thing is to replace only what we are missing. Replace missing populations on boundary. Okay, so these guys are not actually that popular. This is always, so what you learn when you become a teacher, you always have to start with the things that are not popular, because when you start with the popular things, then nobody listens to you once you introduce the ones that are not working that well, right? So this is why you should always hear the story to the end, right? Because the good stuff comes at the end, and the boring stuff comes in the beginning. It's unfortunately the way it is. Yeah. So node-based boundary conditions, they depend very much on the orientation. On the orientation of the boundary. So you have to specify them again and again, depending on their orientation. And they are usually often only available for special cases. So for example, your domain may have has a boundary on the left-hand side, but it will also have corners in the upper left and upper right corners and so on. And these boundaries are often not specified for corners. Yeah? And now this is the simple case in 2 dimension and flat surfaces. In reality, we have in 3 dimensional, we have curved surfaces, right? So this is, then it becomes more and more complicated. And to actually specify this kind of boundary conditions, and this is why they're not actually used in practice that much. Of course, there are also people researching these kinds of things a lot, and they may disagree with me, but I mean, we are also dealing a lot with the practice, so I can tell you these things are not very common. But the one that you will find in your books, in the textbooks, especially if you read the Krüger book, is of course the Su and her. Yeah, the guy is called her. Yeah. Well, I mean, my Chinese is obviously. I mean, I cannot speak Chinese. I just know that it's not he. Yeah, so it's something more like her. Sorry. So Su and her, they introduced this. Okay, you know this thing is much older than I guess you, right? I guess so. No? 95. Okay. Okay, older than some of you, I guess. Yeah. Okay, so this is what they did is, and now we have to, because they are very specific, we have to draw something. So let me draw this lattice. So they have a little bit of different nomenclature because they are archaic, obviously, so they have a little bit different nomenclature from mine, but I try to do it in my nomenclature. So the boundary is on the left, right? So this means that we have missing information going to the right. Yeah? So the distributions that enter here from F1, and F1, 0 and F1 minus 1, yeah, they come from outside, so they are not known. So we have to specify them. And they are to be specified before collision. I mean, this is one of these things why this doesn't work, by the way. So this F11 and F10 and F1 minus 1, they are unknown before collision. Where the others are all known, which only works if you have a nice flat wall, right? There are no corners or something, but this is the assumption. Okay, then at this boundary we want to specify both density and velocity, and you immediately notice that this is a little bit, other than in the Navier-Stokes equation. So they would probably say, hey, wait a minute, I want either to specify a velocity boundary or a pressure boundary. This is a velocity and a pressure boundary, okay? So a little bit specific here, but this is the way it is. So, and actually it's not even a velocity boundary, but it is a momentum boundary because it is ux times rho that we specify. And this is specified by computing the moment, and so this is, yeah, I omit the lattice units here, yeah, because we usually do this. Okay, moments without lattice units, right? So I write the guys that are not known, I put them in these brackets, otherwise the bracket has no meaning. Just a guide for your eye, so to speak, minus the other ones that go the other way, minus F minus 1 minus F 1, 1, right? So this is how we compute the velocity. Then we have our equation 7.2. So that's the x velocity. Then we specify a y velocity. The y velocity is the sum over I and j, jfij. And this has a little bit different structure. So we have only two of these distributions, and this is the difference between them. Plus f. I mean, one thing that's crazy about this boundary condition is that the distributions that run parallel to the boundary, they are kept as simulation variables, which is also not necessarily completely, I don't want to say correct, but it's not intuitive necessarily, right? So, and then 7.3, we also have to specify our density, which is, of course, proportional to our pressure, Fij. So this is just the sum over all the distributions. And this means here we have F11 plus F10 plus F1 minus 1. And all the other guys, oh god, F minus 1 plus F minus 10 plus F minus 1. So I hope that I write all of them. Otherwise, I guess that you are clever enough to correct my mistake. So, what we notice is that this guy and this guy here is the same, right? So, we can solve one of them for the one and put them into the other. So, we have the consistency. Consistency between 7.1 and 7.3. which leads us to 7.4 as rho minus, so I put, which one is this? This is 7.3, so I put everything on one side, and I solved 7.3 for the thing in the bracket, right? And put everything here, 1 plus 1 and f01 plus f0 minus 1 plus f0, 0. So I have not checked it. If I missed something, then I am confident that you could correct me. And we put this, wait, I miswrote this in my notes. So we take now the equation 7.1, yeah, which is ux rho, and here we have 1 minus 1 minus 1 plus f minus 1, 0 plus f minus 1, 1. So now we reduced these three equations from which we started to two equations. We are missing three distributions, so now we have two conditions left, so we have to specify a condition which we do not know, and now these guys made an assumption. They just made this assumption. And I point out that in a different case, so for example in 3 dimensions or on a different lattice, they have to make a different assumption. Yeah? So their assumption here was, which I believe they call non-equilibrium bounce back for whatever reason, is to say that the non-equilibrium part of the particle going directly in x direction is the same as the non-equilibrium part of the guy that is going the opposite way. Right, so this is the assumption. So this gives us an additional equation. And what we now do is, I'm not demonstrating this, is we solve 7.2, 7.4, and 7.5 for the missing distributions. That are these ones, and this gives us the boundary condition. Okay, so no, this is actually was supposed to be. There's not a lot of positive things to say about this boundary condition. I don't get it dead, and I'm even addressing it in my lecture. Maybe this is my fault. So they are difficult to generalize to other orientations. For example, corners or other lattices. So they work in 2D, so what is this good for? I mean, I have to tell you, the Lattice Boltzmann code that we develop here has no option to run in 2D. Yeah, I mean, this is we do 2D only for exercise with students. There's no other reason, yeah, or for demonstration. This guy here is also very unstable. I don't know whether you noticed this, but you're not going to extreme resolutions, I believe. Very unstable. So now, of course, you will find it prominently in textbooks. In particular, the one that I believe many of you have looked into, the one by Krüger, but they are not in practice. So I don't want to, by the way, this is not a critique. I mean, this is important to note that these guys exist, and I don't want to critique the book. I actually didn't read it, so I can't say that much about it. I mean, it's a good thing that there is this book, of course. Okay, sorry for, let me see whether we can somehow do this, because here comes now the important stuff. Link-based boundary conditions. So, now we did something that you may be familiar from Navier-Stokes and from other cases. You have a node and you put your boundary there. So this appears to be very natural, yeah, but not in Lattice Boltzmann. And the reason for this is that we actually have this shift in our locations and in our time step. Yeah. So what we do is we often put boundary conditions halfway between nodes. The same way as we put our distributions halfway between nodes. And this is probably something that you learned from me and not from the book. Yeah? Because this is already it's 10 years old, but Lattice Boltzmann is something like 30 years old, right? And 10 years ago, Paul Deller described this way of interpreting Lattice Boltzmann as trunk splitting. So this is something that we did not properly introduce here, but this is actually this idea to do half steps, yeah, in order to get second order convergence or consistency for splitting schemes. And we have a splitting scheme because we have collision and we have streaming. So we have to split something, and this is why we end up with these half steps. But it was a long way to come to these interpretations. So if you read the books and the papers, you will probably find it completely differently described. So let me put here, I get a little bit more spacing now, my lattice nodes. And here would be the next lattice nodes, but we have our boundary in between them. And now distribution would go here and would return here, for example. Yeah? So and here we have our boundary condition. I have to switch my pen. So the easiest thing to do is now okay, this is not the correct color now. So say we have F1 here, and this is the post-collision state. Then we specify F opposite pre-collision state. So if we just mirror this, we obtain the so-called halfway bounce back, which is already a very useful boundary condition, bounce back. This is just mirroring the outgoing distribution in flight so that we can specify, so just take this now as an I, yeah, so I inverse, yeah, so the one coming in is xn, so okay, so this is xn, this is the one on the boundary, yeah, xn. So I specifically not write boundary condition, because the boundary condition is not on the node. This is important to know, yeah. Xn is in the next time step, yeah, so if this is t, and this here is of course t plus delta t. So in the next time step is the post-collision state of the oppositely moving, the one that is moving out, at the position xn and in the previous time step. So, and what this does is it produces a zero velocity, so bounce back, I write this capital because this is a name, is a so-called no-slip boundary condition. No-slip means it is setting velocity to zero, and both depart normal and parallel. Everything, so it's non-penetrating and it's not slipping. Okay, so there are others, but one thing that again, I'm not sure that this is written in the book. As I said, I didn't read it, but this is something from the practice that I believe is not mentioned in writing that often, is that there is a slight variation of this boundary condition, which we usually find useful. To draw this a little bit further down. And this is the so-called delayed bounce back. So again, we have x here and we have t here. And again, we have here the would-be nodes, and here's the wall. So what we do in this boundary condition is we let the distribution actually go into the wall, and from here we let it go out of the wall again. So this is now the opposite, but pre-collision. So we get from this Fi is, again, this is xn. So xn and t plus, now because it went into the wall, it waited for one time step, it comes out two time steps later. And this is, so sometimes you see it's applied like this, and my problem is I'm running out of time for today, and because we are anyway, we missed so many lectures, I want to get some things across, so I'm not going into detail here, but if you ever run into problems with stability, you may consider this thing here, because this is more stable. What you observe, so very briefly, what you can observe with the usual bounce back is that it has a tendency to produce oscillations, grid space oscillations. And these grid space oscillations are cancelled out if you just wait one time step. So the observation is that you can increase the stability of your code sometimes quite considerably just by delaying the bounce back. Yeah? And so many times simulations didn't run very well was because they used the wrong bounce back. In principle, this is inaccurate. Yeah, so this comes back one time step too late. But as we'll I don't know, hopefully see at the very end of this lecture, this is not something that we have to worry about that much. So one addition to the bounce back family is that bounce back can not only deal with velocity zero, but bounce back can also be used to specify any other velocity. So velocity bounce back, boundary condition, which is a generalization of the bounce back boundary condition, and it can be done with all forms of bounce back. So the two ones that we have seen and the two ones that I still want to mention. So this addition can be done to all of them, right? So when we have Fi x xn t plus delta t. So now I, just as an example, use the first one here. This is equal to Fi, the post-collision state at the previous time step. And then we add we add a modifier on the velocity, which is 2 theta, the lattice weights that we know from our BGK collision operator in the equilibrium. And this we multiply with the lattice vector. Now I write it only with one indice here, so you can write it also with multiple indices. I've written it only with one here. Scalar product with the velocity that you want to impose at the boundary. Yeah? So this theta is the speed of sound squared in principle. This is this 1/3. And Wi are the lattice weights. And with this modification, you can specify any velocity that you want using the boundary condition. And this also works for some modifications. By the way, do you guys have a few minutes more for the lecture, or you want? Okay, this would be, because I mean we have to run overtime because we spent 20 minutes in the discussion before. Otherwise, I'm not. Sorry. Now I even missed my point. So what is becoming interesting, and this is a little bit beyond the homework. Yeah, beyond the homework is, maybe this makes it less interesting, but I hope you're very interested. Beyond homework, so we have off lattice boundary conditions. It means this is the way out of Lego land. Because we are, in Lattice Boltzmann, we appear to be in Lego land, yeah, because we have this Cartesian grid, and we want to have boundaries anywhere, and this is possible with so-called interpolation bounce back. And again here, I want to specify 2 of them. There is now a lot of them, especially in the last 10 years. So probably, one thing that is bad about the book by Krüger, and this I mean without criticizing the book in general, but it was written at a time when there was a lot of changes just during the writing of the book and a little bit later, and write even more changes than there are now in the whole subject. So it was written in a time where it was missing a lot. Yeah. So just in the last few years, there had been a lot of these kinds of boundary conditions. A few of them were before, and this one obviously was an early one. So this is in the book, obviously. Is the one by Bosidi. And he introduced the so-called subgrid distance, which we are still using today in other boundary conditions too. And the subgrid distance is usually called Q. So what is Q? Q is the fraction. It is not a distance by itself. It's a fraction of the vector AE delta x between the last grid node and the wall. So obviously, so Q is always between 0 and 1. So, I mean, or even for a direction that goes diagonal, where you should say, so the length of this link is square root 2, but the Q that's specifying it, because it specifies the fraction of this length, is always between 0 and 1. So don't mess this up. And this early boundary condition of this kind was distinguishing 2 cases. This is why you have to write a lot, unfortunately. Later boundary conditions are simpler. So they distinguish between the q being smaller than smaller than 1/2, and q being larger than 1/2. So there are these two cases that we draw. By the way, if you look in the paper, and also we discussed this with regard to the report that you were preparing, yeah, you notice that this characteristic diagram is a little bit my own way of writing things, and is often not written in this way in the paper. So they only specify space and try to specify time by drawing several pictures. The characteristic diagram always specifies space and time, and so I think that it gives you a better overview, yeah, of what you are actually doing here. So the first thing is that q, so this distance here is q delta x, and this is now smaller than 1/2 delta x. Yeah? So what you want to have is you want to have an incoming distribution at this place. So an incoming distribution at this place would come from here. Yeah, because we are doing bounce back on this, in this position here. Yeah, and the entire distance traveled is 1, right? So this means if this here is q, then this here must be, okay, so this is very, so this length here, is actually delta x minus 2 delta x q, yeah, because the entire length of this path is 1 delta x, and it goes q to the wall, and it goes q back, so it's delta x minus 2q, yeah. And what we are now doing is we're interpolating between these two nodes here in the last time step to this place. So because this here is delta x minus 2 delta xq, then this means that this here must be the length 2q delta x. And now we do linear interpolation. So for q smaller than 1/2, do linear interpolation fi delta x comma t plus delta t. Linear interpolation, so this here, as we so this is just the, what is it called, the Waage. Yeah, you take the one length, yeah, the lever, yeah, right. So this is the lever law, because it's a linear interpolation. So it's 2q fi, the post collision of xn and t, so this is the one that's going into the wall, plus 1 minus 2q fi post collision xn, and minus ei delta x and t. So this is the minus xn ei, this is this position here, xn minus ei delta x. Yeah, so this is the previous node. Okay, so this is okay. I probably draw the other case. No, I wanted to draw the other case next to it. I still have the space, so I'm going to do this. So this is x and t, and say this is now the. Okay, I'll do it this way. So the other case is that the wall is closer here, so that this delta x q is larger than 1/2 delta x. And in this case, we do it a little bit different. So what we do is we go here, right, land here, and then we do the reflection, and then we notice this is outside our last grid node. So we take into consideration that another one guy is here, and we do the interpolation now. We now do the interpolation because we want to have this distribution that is coming in here. So this is the one that we are looking for. So we interpolate this now not from the previous time step, but from the coming time step. And we notice that this here is the length delta x. And this down here, this guy here has the length delta x minus 2, 1 minus q delta x. So it is equal to 2q minus 1 delta x. So this means that for q larger or equal to 1/2, our boundary condition is fi delta xn t is 1/2 q fi post collision xn and t plus 2q minus 1 divided by q fi asterisk x n and t. So, guys, do you want to hear the one-point interpolation boundary condition? Yeah, so unfortunately we get a little bit into the lunch break today. I'm very sorry. But anyway, one-point interpolation. This is something that is actually now in use. So this is the way it is currently done in practice. The one-point interpolation boundary condition. So again, we have this picture. I'm probably not drawing very beautifully if I try to hurry up. So the one point, we previously had to distinguish between different cases. So this boundary condition does not distinguish between cases. So it does not matter. I just draw my boundary somewhere, yeah. And still, this here is delta x q, and of course, as always, this is x and this is t. So what we are going to do here is we make, let me see, we need an xn. I call this here an xa in lack of a different wording, and this xb and c, and this here I call xv as the virtual node that would be inside the wall. And what we are interested in is to do a bounce back at this position again, right? So first thing that we have to do is to get the distribution at this point, and this we do by linear interpolation along the characteristic, yeah? So this is something where this diagram is very useful, because we use this diagram in space and in time, and we cannot only interpolate in space as Busidi did, but we can interpolate in space and time at the same time, right? Because we are moving in space and time, which we call a characteristic. So we do a linear interpolation along a characteristic. And this leads us to the boundary. So at the boundary, the fxbc and at the time t plus q delta t. So because we are moving, so this here is q delta t. Yeah, we don't have only q delta x, we also have q delta t in the other direction, obviously. T plus q delta t is fi is equal to fi x n and t times q plus fi, so at the virtual node, and t plus delta t, so this is the next time step, 1 minus q. Okay, so we are looking at the pre-collision state. So what is the pre-collision state at the virtual node, at the next time step? What is this? The one that is in the pre-collision state at the node next time step in the node in the wall. What is this? How do we know this? So how do we get a pre-collision state anyway? Where does it come from? Because we always have to have our pre-collision state, otherwise we cannot. So somewhere the pre-collision state has to come from. Well, we do streaming, and what was the pre-collision state before? Yeah, so then it was the post-collision before of the. So it was the post-collision where at n, yeah, and at the time before, right? So it was at the node where we later want to specify it, and at the time before. So we can replace this guy here simply by so this is an interpolation between the pre-collision state and the post-collision state on the same node, right? So because you see that going to the boundary, fi at the boundary BC, t plus q delta t is nothing else than fi xn and t times q plus fi post-collision xn t and 1 minus q. I'm going to call this equation 1 now. Now, what is important here? So previously we had to interpolate between the distributions at node 1 and distribution at node 2. What we do here is interpolating between pre-collision and post-collision, right? But they are both at the same location and at the same time. So this is obviously very useful. So what we now do at the wall is we are doing a bounce back at the wall, which is simply we turn this thing around. Bounce back on wall. Bounce back on wall, and this simply means we have an fi going to the opposite, BC, t plus q delta t is equal to fi xn t and t times q. What am I writing? Yeah, so I'm writing the same thing as above. So this is wrong in my notes. Fi xn and t and 1 minus q. Okay. So now we are here. So from there on, we want to get to this place, and we do this by an interpolation from this location to this location. And for this, we take the link that is going here. So so we are looking for the distribution I going the opposite direction, but not on the node, not on the boundary, but on the node. Yeah? So, and this we do by interpolating between f now at the position A. So, okay, unfortunately we are running, this is now running out of space. So A is the node next to us, yeah? Next to the boundary node, xa, and time t plus delta t, so in the next time step, and the one that we have at the boundary, so there's an I, there's an I bar, so because it's going the other way, and the I bar, other way, that is already used to bounce back, t plus, so the one that we have is t plus q delta t. So, and the way this looks like in equation form, fi bar is xn, and t plus, so, okay, we're a little short in time, obviously, or we are a little over time, or we are a lot over time. Therefore, I just take the freedom to write most of this down. Now we do the interpolation in space and time. So we have t, we come to a strange place in time. We have x, let me see, is xa, is this xa, yeah, I hope so. T plus delta t, so taking again the leverage, but not the leverage in space, but the leverage, in space and time. This goes to q plus 1, because now the entire distance covered, because this distance here is delta x and the other one is q, right? So this is q plus 1, and this comes plus fi at the boundary that we just computed, t plus q delta t. So in the time, the time is of course here the interpolation between the times here, and this is you see, this is for one it is delta t q divided by q plus 1, so this is the first one, and the other one is t plus q delta t times 1 over q plus 1. This is also q, this is also the same thing, and what, you're right, so I've already drawn it here, so this is leading us to this position here in space and time. And what we still have to specify is this guy. So what is this guy? Again, because this is in the next time step, and it's the pre-collision state at the position A and t plus delta t. So the same question as before. This is the post-collision state at the node itself in the previous time step, yeah, because it's going the other way, yeah, and here we want to interpolate this. So then introducing equation 1 into this gives us fi opposite direction xn t plus 2q delta t q plus 1 is equal to q divided by q plus 1 fi post-collision xn and t plus fi xn and t in q and q plus 1 plus fi post-collision xn t times 1 minus q divided by q plus 1. So the important thing here is now that everything on the right-hand side is strictly depending only on xn and t. The only problem that we have is that our boundary condition appears in the wrong place in time. Yeah, because there is not delta t as it should be, t plus delta t, but it's 2q divided by q plus 1 delta t. However, we are only looking for second order consistency, and we are using diffusive scaling. And what does diffusive scaling mean for the time? Diffusive scaling means delta x is equal to epsilon square. Delta t is equal to epsilon square. So because the linear spatial interpolation is only second order consistent in delta x, so this time offset is only as inaccurate as the linear interpolation anyway. So these errors in time are not important. And so 2q divided q delta t, this is close enough to delta t that we now can specify our boundary condition. And as I said, this is something that is actually in use. This is xn t plus delta t, so we just ignore this and write this as fi asterisk xn t, so everything dependent just on the node itself. We just have to distinguish it between pre and post-collision states, q plus 1, and this plus fi asterisk xn t 1 minus q and q plus 1. So thank you for staying with me for this 20 minutes overtime. Okay, I'm stopping the recording. Does it work?